we deal with things that just happen to be moving in a circular path, not things that are spinning. Okay, and there's a big difference in how we look at those objects. But circular motion is just things that move in a circular path. Okay, so we're going to talk first about the kinematics of circular motion, then we're going to move into the dynamics of circular motion. Kinematics, remember, is how things get from A to B. Dynamics is why things get from A to B, right? One is motion, one is forces. So what is it that causes an object to move in a straight line? What causes an object to move in a straight line?
Force.
A force, right? And give me more specifics about that. A force causes it to move in general. Well, what causes it to move in a straight line? An applied force? Kind of. You guys are thinking too much.
Constant.
It's got to be a force in the same direction as the motion. That's it. Right? A force that is being applied in the direction we want our motion to go. Right? If I want to move east, I have to apply a force to the east. It's that simple. But circular motion doesn't resemble that. Doesn't move in a straight line path, right? It moves in more of a projectile type path. Okay? But that projectile keeps going. So what does it take for an object to move in a projectile? A force applied at an angle, right? A force applied at an angle. So if your net force is at an angle, now we've got our motion going in this like parabolic type path, right? A projectile motion path. So we need to think about a little bit of the differences here between straight line motion and circular motion. Objects that move in a circular path or in an orbit, or however you want to talk about that, has more similarities to projectile motion. Okay, we're not necessarily going to use our kinematics equations for projectiles, but it's got more of that, parabolic type path. Sorry. Okay, this is just kind of an introduction to circular motion. I hope you guys understand by now. You don't have to write things down word for word, right? Wait for the equation. Okay. So when we look at circular motion, we are going to look at uniform circular motion. What does it mean to be uniform? The same. Good. The same throughout. So uniform circular motion means we're not looking at objects that are speeding up or slowing down while they're moving in a circle. Okay, they are moving at constant speed. That's important. Okay, our objects that we're looking at in circular motion are going to be moving at constant speed. Okay, so that means that X's out all of our current kinematic equations. Right, all of our current kinematics equations have an acceleration in them. So we're going to change or shift our kinematics equations for circular motion. So, we said it's got to be moving at constant speed. Constant speed does not mean the same thing as constant velocity. Right? Velocity has to have two things. Magnitude, which is speed in this case, and direction. So, why do constant speed and constant velocity not mean the same thing? Yes, speed is just the magnitude. Okay? It's the distance per time. But the direction component means that our velocity can be changing even if we're moving the same speed. Okay, and that's kind of like it's a little bit counterintuitive. So technically you have a change in velocity. All right, so in our circular motion, the magnitude of our velocity remains constant, but the direction is constantly changing. Okay? The magnitude or the size or the number, however you want to write that, it stays constant. The direction is constantly changing. Okay? Continuously changing. Maybe I shouldn't use the word constant. So we've said we've got constant speed but not constant velocity. And we know acceleration is the change in velocity. So we still have what we call it, we're going to give it a different name here, but it's still acceleration. So since our velocity is changing by direction only, it's still changing, we have an object that is constantly accelerating. Okay? It doesn't necessarily mean it's speeding up or slowing down, but its velocity is changing, which causes an acceleration. Okay, so this kind of warps the way we've looked at acceleration thus far. Right? So far, we've only seen acceleration mean we're speeding up or slowing down. Now we're looking at it as purely in a change of direction. I'm going to pull up a picture that's in your book. Textbook you can. This one's actually on 113. Okay. So you don't have to necessarily write this part down, but I want you to look at it and I want you to think about what I'm saying. Okay? When we look at the path of an object that's moving in a circle, right, we're essentially looking at infinitesimally small amounts of time that they're moving in a straight line, right? But that straight line changes position with every millisecond, every nanosecond, whatever it is, right? We're changing position as we go around that circle. Okay? So essentially we're looking at really, really small time intervals. When we look at velocity, we're only looking at velocity at that certain point in time. So if I want to know the velocity of my object at this point on my circle, right, or at this point or whatever, I'm looking at what we call the velocity that's tangent to the curve. Okay, so let me explain what this means here. If I want to look at my velocity as my object is swinging through the air, right, if I have my object that's moving in a circular path, and I want to look at what is my velocity, how fast is it moving at any point in the circle, I examine just that little point. And I say, if my object were to leave the circular path at that point, what direction would it fly? Would it keep moving in a circle?
No.
No, it would move in a straight line, right? So if I'm not going to do this, but if I am swinging this in a circle and all of a sudden I let go, is it going to just magically keep moving in a circle? No. Whatever point I decide to let go of my object, right, it would move in a straight line at that point. Okay? Or if I let go of it down here, it would move in a straight line that way. That's what we call the velocity tangent to the curve. So at any point here, if we let go of our object, it would move in a straight line from that circular path. Okay? That's what we call tangent to the curve. This goes into a lot more math than I care to know about or really think you need to know about, so I'm not going to do it. If you want to do it, great. If you want to follow along with the derivation of it in your book, great. Not going to do it. Okay? So, essentially what you need to know is that if we were going to look at a velocity of our object, when it leaves the circle, that's called our tangent velocity, right? Tangent to the curve. Okay? And again, if you want to follow along the math that gets us to this equation, go for it. Not going to do it. Okay? So this equation, A sub r, tells us what we call our radial or centripetal acceleration. Okay? Radial acceleration is, they label it with an R. Okay? And that tells us how quickly is our position changing, essentially. Right? How quickly is our position changing? So we say v squared over r gives us our new centripetal or radial acceleration. It has to do with the triangle in the last diagram. Don't need to know. Okay? But here's our equation. Equation number 1 on your new equation sheet. Or old equation sheet, whatever. Okay. So what this equation tells us, in plain words, says an object moving in a circle with radius r and constant speed v has an acceleration whose direction is toward the center of the circle. That is a little bit less clear for us, but we need to understand that as we have these objects moving in a circular path, if I try to move that object at the same speed, but I just decrease the radius, what happens to my acceleration? It gets increased, right? As I decrease my radius, as this number gets smaller in my denominator, my acceleration increases. I'm covering a greater chunk of the circle in the same amount of time, right? So as I try to move at constant velocity and I decrease the radius, right, my tangent velocity is theoretically the same, right? I try to keep it theoretically the same, which means it leaves the circular path, it's going to travel at the same speed, but it's covering a greater chunk of the circle at that time. Okay, so that's what we call centripetal acceleration, or radial acceleration with an R. Okay? So as the radius of the circle increases, the acceleration increases. As the radius decreases, acceleration increases. Yeah, I said it backwards. Okay, as radius gets bigger, acceleration gets smaller. Okay, and vice versa. Okay, so they use two different words for centripetal and radial acceleration. They mean the same thing. Okay, they call it centripetal acceleration, but then they label it a sub r. So don't ask me why your book does that, but they do. Okay, when we draw our centripetal acceleration, we draw our velocity vector outward, right? We draw our velocity vector tangent to the curve. So as my object is moving in this direction, and it would happen to leave the circle, it would travel there. Right? That's tangent to the curve. And when we say our acceleration is always center seeking, right? That's what centripetal means, center seeking. Those two make a right angle. Okay? When we draw our vectors, they have to always be perpendicular to us. So as long as we draw our velocity vector tangent to the curve, right, that means in a straight line from our circular path, our acceleration always is center seeking, so it's toward the center of the circle. Those two should form a right angle, okay, or should be perpendicular, always. All right, next two topics we're going to look at is something called period and frequency. Have you heard these two terms before? Kind of, okay. Period and frequency. Frequency is a lowercase f. Anyone know what the units for frequency are? Hertz, good. Okay. Or revolutions per second, or revolutions per minute, or whatever you want to say. But revolutions per second is also called a hertz. Okay. So what that tells us is how many revolutions can it make in 1 second. Okay, so frequency is lowercase f, revolutions per second. That's important that you know the units and the difference between these two. Because period is a capital T, and it is the time required to complete one revolution. So it is seconds per revolution. Okay. Frequency is revolutions per second. Period is seconds per one revolution. They have this relationship described in this equation. So this needs to go on your equation sheet. So I want to try it just with simple numbers so that you can see the relationship. If I have an object that I know makes 2 revolutions in 1 second, okay, 2 revolutions in 1 second, that's its frequency. Its frequency is 2 revolutions per second. Okay, so in 1 second it goes around once and it goes around twice. What would its period then have to be? How long would it take for it to make 1 revolution? Half a second, right? It takes 1 second for it to go around twice. So in order for it to go around once, it would take 1 second. So that means its period would be 1/2 second per revolution. See the reciprocal of those? That's all it is. Right? It's a reciprocal relationship. So this equation needs to go on your equation sheet. It also works like this. F equals 1 over T. Right? You can have either version on there. Okay? It is really important that you know the difference between those two things. Period is always measured in seconds, okay, or in minutes or in hours, whatever. It's the time per revolution. Frequency is revolutions per second or revolutions per minute or whatever. Okay? Do you guys know what RPM stands for? Revolutions per minute. And where do we see RPMs a lot? In cars, right? So some problems might be written in revolutions per minute, right? Which means you might have to do a conversion or something. But just something for you to look out for. Okay? Okay. This first equation, I hope you recognize, since I wrote it up here, that it's for the circumference of a circle. Why do you think we would need to know the circumference of a circle? What does that tell us? Okay. All right. Okay, maybe. The circumference tells us the distance we travel one time around the circle, right? So if we want to find our velocity, we need to say it traveled this much distance in this much time, right? Period is the time it takes to make one revolution. So connecting period, the time it takes to make one revolution, gives us our velocity. Okay, does that part make sense? How those equations are coming together? Circumference is the distance around one revolution. Velocity is always distance over time. So this equation here tells us that for objects at constant speed, we can put period and velocity into the same equation. Okay, so you need to have this one on your equation sheet as well. You probably don't need the circumference. You're never going to use that really on its own. But you do need that bottom equation. Does everyone understand kind of where that equation comes from? Okay. A check on our units here. What does radius always need to be measured in? Radius needs to be measured in meters. We still want our velocity to be meters per second. Okay, this needs to be meters. Period should almost always be measured in seconds. Not almost always. It should always be measured in seconds. Okay? All right, let's try one. So far, have we had any equations in this chapter that include mass?
No.
Not in this chapter so far. Nothing so far in this chapter that includes mass. So we don't need the mass for right now. When we deal with the forces behind it, we'll include mass. But for right now, we don't need mass. Okay, it tells us it's revolving uniformly. It's got a radius of 0.6, so we keep that in 0.6 meters. It tells us it makes 2 revolutions in a second. Is that period or is that frequency?
Frequency.
That's frequency, revolutions per second. So frequency is 2. We want to find out its centripetal acceleration. Okay? So I put our equation over here. Centripetal acceleration, remember that's the same as AR. AR and radial acceleration are the same thing. Okay? So in order to find that, we have our radius, we don't have velocity. Okay, so we need to use our 2 pi r over t to help us find velocity first, and then we can go find acceleration. Does that make sense? It's a 2-part. So we need v equals 2 pi r over t, that equation first, and then we can go plug that in for velocity. Okay. So velocity equals 2 pi r. What do we know t is?
1/2.
T is 1/2, right? Because t is equal to 1 over f. And we know f is 2, so t is equal to 1 over 2, which equals 0.5. This chapter involves a lot of that finding and then substituting or whatever. You know, it might be multiple steps to get to our final answer. I don't care if you use the pi button or you punch in 3.14. It's not going to make a big difference. Is that about what we had? 7.54? For velocity. Just velocity. From there we can move to v squared over r. So we would say A equals 7.54 squared over R. There's a couple things that should jump out here. Right? We know our radius is in kilometers first. What needs to happen? We need to put it to meters. That's right. We just add 3 more zeros onto it. So this value right here, it tells us it has a period of 27.3 days. Okay? Anytime it's just given to us in a time, like that's got to mean that it's period, right? It's not revolutions per day. It's given to us just as a time. Okay? So days is a long amount of time, but it gives us to it, that means that it's period. So to get that to seconds, we take 27.3 times what? Times 24, then times
86,000.
all right, there's lots of ways you can do it. 24 hours times 60 minutes times 60 seconds, right? If we want to go from days to seconds, we go 27.3 times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute, right? That's where we're at. But the period comes out 235.8720. Yeah. Okay, so all we did was convert days to seconds, right? You can set it up in a full T-chart, but by this time I think you guys should be comfortable enough seeing what that looks like. Okay? So days to hours to minutes to seconds. We want to find acceleration, which means we'd use v squared over r. We don't know the velocity that the moon is moving, so we find that first. 2 pi r over t. Is that about what you had for velocity? All right, so now we're moving into the dynamics part of it. So why does an object move from A to B in a circular motion? So I've got kind of a derivation of equations here, and you don't have to write down all of them, but I want to show you how I got from 1 to 3, okay? This equation, centripetal force, okay, or radial force. Centripetal force here is mass times centripetal acceleration. Okay, what does this equation look like?
It looks like gravity.
Kind of. It looks like F, almost net. No, F net. Looks almost like F net, right? Newton's second law tells us that force is equal to mass times acceleration. So all we're doing here is applying this to our circles. Okay, centripetal force is equal to mass times centripetal acceleration. So this is one you need to have. Okay? The second one you already have. Tells us that centripetal acceleration is v squared over r. So if I want to put these two together, I say centripetal force is equal to mass times v squared over r. So you need this one and this one. You should already have the middle one. Okay, so yes, all of those need to be on your equation sheet somewhere. Centripetal force, just like all our other forces, should be measured in newtons. Good. Mass should be measured in kilograms. Good. Acceleration is still meters per second squared. Still meters per second squared. Since we were told previously that our acceleration is center-seeking, that means our centripetal force also points toward the center of the circle. Okay, it also points toward the center of the circle. Okay, this centripetal force is not like necessarily something new. It's given the name centripetal because it's always changing direction. Okay, the direction of the force always changes as our object is changing. Okay, and it's always changing to be pointing toward the center of the circle. Open your textbook to page 115, and I want you to look at figure 5.4. So this is really similar to the problem we already did. We actually already found the velocity for this problem. Right? We already solved this exact problem. Find the force a person must exert on a string attached to a 150-gram ball to make it rotate in a horizontal circle. Good guess. All right, so did we find the velocity already in a previous problem?
Yeah.
Yes. What was it?
7.54.
Okay, and we already found the acceleration, right? 94 something? 96 something? What is it?
94.74.
Okay. So we already found the velocity and the acceleration from the previous problem. We don't need to have necessarily both of them, but we know that Fr is equal to mass times A, and we already have A, so we might as well just use that one, right? So to find my centripetal force, I take mass, which is 0.150 times 94.7. .2 newtons. Okay, that's it. These problems are very much like plug and chug, right? Plug those numbers in, you'll get an answer out. There's not a whole lot of problem solving like there was with our inclines and all that kind of stuff. It's pretty much straightforward. So this rotation, or this ball revolves 2 times every second. 2 times every second. Is that your frequency or the period? That's frequency. So frequency is 2, which means period is 1/2, right, or 0.5. I can say centripetal force, which is the same as the net force, equals all positives minus all negatives, right? It's the same situation here. Do we have anything that's pushing us in the positive direction? No. No. But I want you to think about, sorry, I left out one little tiny detail that's going to make a difference. Okay, in our circular motion, we said acceleration and net force are always pointing toward the center of the circle, right? Yes. Recall? Okay. So, I don't know who chose this or why we do this, but the center of the circle is considered to be the positive direction. The center of the circle is considered to be the positive direction. Okay? Because our acceleration and our forces point toward the center of the circle, they choose the center of the circle to be the positive direction. So, in this case, our positive forces are both tension and gravity, because they're both pointing toward the center of the circle. Okay, so sorry I left that little detail out earlier. But the center of the circle should be its positive direction. So these are both pointing toward the center, which means both technically positive forces. Okay? Now we can go about solving for it. If we know our object is at the top of its motion, what do we know about the tension in the stream? Right? It's the minimum that it can do without falling out. So technically our tension would be what? 0. Right? We want the least amount that it can do. So our tension is 0. Okay? That's only specific for this problem because we're looking at the minimum speed. Right? If it was just looking at the maximum speed, you would have to be given a tension there. Okay? Minimum speed means tension is 0. Fg is always what times what? Mass times gravity. Okay, then what can we substitute here? We can say m times v squared over r. And we're solving for v. So I'll take 0.15 times v squared over r, which is 1.1. Why am I not splitting 1.1 in half to find the radius?
Because it's at the end of the chord, and that chord is essential.
Very good. So the chord, right, that's 1.1 meters long. I know my string's invisible, but okay, if it's 1.1 meters long, that is my radius, right? So as it rotates, that whole length of the chord is to be considered the radius. So don't split that in half. So go ahead and do the algebra. We need to solve for velocity. Algebraically, are we getting it to come out okay? 3.3, 3.28. If you didn't write down this diagram, you're going to want to do that. Okay, we're going to have problems that look like that a lot. If it's at the top of its motion, you need to understand we add tension and gravity. If it's at the bottom of its motion, which we'll do in a second, it looks different. This time, I would say centripetal force is equal to the force of tension minus the force of gravity. Right? Tension's not 0 in this case. I'm trying to find how fast it's, or I'm trying to find how much tension is in that stream. Okay, so that's what I'm solving for. Yep, same everything from the previous problem. Same mass, same radius as the previous one. Trying to find tension. And I know this time my velocity is equal to what?
Twice.
3. Twice. 3.
Yeah, 3.3 times 2. Okay, it depends on where you round it, that's fine. 6.56, 6.6, that doesn't really make a difference. Right, that is mv squared over r. That comes from that substitution. I'm solving for tension, and I know that Fg is mass times 9.8, which is 1.47.
What's the F smaller?
You need to know the difference in the diagrams from when our ball is at the top of its arc or at the bottom of its arc. You need to know, are they working together or are they working apart? Okay, or against each other. You try this one. Try this one on your own.
That's a big rock.
Mm-hmm. First thing that you want to do is look at your diagram. It's at the top of its motion. Right, both of those are pulling toward the center of the circle. What do we think this 2.4 newtons is telling us? What is that?
Tension.
Tension, good.
Oh, Lord.
How do you find the force? Oh, okay.
Jack, did you get 3.1 for velocity? Yeah. So 2.4 plus 6
If we look at our object, I'm going to show you kind of like a bird's eye view of this free body diagram. Okay? This is like a going around a curve, right? Here's our car. Right? This is a bird's eye view, so this is from above. Are we all understanding what's happening here? Okay? Our centripetal force is always center seeking, and our frictional force is what's opposing that motion, right? Or opposing that force. So those two are in opposite directions. Is that making sense? Yes? No? Maybe? Okay. Okay, so do you see how in this problem, I didn't solve for a variable. I compared my two forces. right? If friction is greater than my centripetal force, that means I'm going to stay on the road. That's what I want. Right, so that means I'm going to safely drive the curve. Okay, so I didn't have anything I needed to solve for, but I'm comparing my two forces. So technically the equal sign doesn't really work. But I'm comparing my two forces. Here's how much force is being applied to make that go around the curve, and here's how much friction is holding it in place. So it doesn't mean it's going to bring it to a stop. It just means that it's safely going to round the curve. Okay? What would happen if my friction force was less than my centripetal force? Then I'd have a problem, right? Then I'd have a problem. So do it now with the coefficient of icy and see what happens. Coefficient of icy, yeah.
What would happen if the frictional force was great?
That's the same case here. Frictional is greater than your centripetal force, so it's not enough to bring the car to a stop. It's just enough to keep it in its circular path. So what do we get for our second one? What was our frictional force here?
2450.
If it was 0.25 times 9,800.
You would go flying on that. You would find out how fast I can push it.
So this one, second one's no good, right? Your friction is not enough to keep it on the road. All right, you got it. So for this problem, it says if the object begins to slip at this certain frequency, at this certain rate of spinning, begins to slip, that means you are looking at the exact moment that your frictional force and your centripetal force are equal to each other. You're looking at that exact moment, right, when it starts to be overcome. Okay, when the centripetal force starts to overcome. So those two are equal in this problem. So you will set them equal to each other, the frictional force and the centripetal force.
Recorded myself saying
Okay, so in this last one, we had to first turn frequency into period. We solved for velocity and got 1.1, and we set centripetal force equal to frictional force because it was the exact moment it started to slip off of that path. So that means centripetal force was overcoming friction. So for that split second, they're equal. So I set up mass times v squared over r equals coefficient of friction times the normal force, and I got my coefficient about 0.59. Okay? I know that was a lot of notes today, but yeah.